Hi, welcome back. We're going to be looking at section 10.2 today, and 10.2 is talking about finding the probability of events that are both independent or dependent, and how we can kind of distinguish between those two things. So let's get started. So the first thing we need to understand is, what does this idea of independence mean if we're thinking about probability? So as they define it here, two events are called independent when the occurrence of one of them does not affect the occurrence of the other. So if we're talking about two different events, and oftentimes they'll describe events using the letters A and B because they don't want to have to write out the events using words. But they'll say two events are independent if the probability that both events occur is simply found by finding the product of them. So if I'm interested in finding the probability of A and B, then I can do that by finding the probability of A and then multiplying by the probability of B. This is something that you'll probably want to put into your notebook and keep track of later, but you also need to remind yourself that this is only if you know that the events are independent does this little formula work. And we'll talk a little bit more about what happens if the events are known to be dependent and what we would do at that time. But let's take a look. So I gave a couple of scenarios here that might help us to understand the difference between independent and dependent. So here are scenarios. We're not using the letters A and B. We're actually thinking about a scenario. And so what I've given you here is, let's consider tossing a coin and then rolling a die. Well, how do I know if those events are considered independent or dependent? Well, there's really two questions you need to sort of consider. You should ask yourself, is it possible for the events to happen in any order? If the order in which they happen isn't important, then the events are usually independent. So considering tossing a coin and then rolling a die, since you could toss the coin and then roll a die, or vice versa, you could just as easily roll the die and then toss the coin, it's a pretty good indicator that those two events are independent of one another. They don't affect each other. And that idea of affecting or impacting one another is the second question you should think about. So does one event in any way affect the outcome of the other? If I toss a coin and roll a die, they won't really affect each other, unless you really want to kind of go down the rabbit hole of saying that when I flip the coin, it might hit the die as it's rolling around on the table, but no. So let's consider a different scenario, though. So if we're talking about parking our car and then also getting a parking ticket, you can't really switch the order of those events around and have it make sense, meaning you wouldn't get a parking ticket if you didn't first park your car. And so obviously the outcomes there are dependent on one another. Getting a parking ticket depends on whether you've parked in a no parking zone or a parking zone. So just a couple of quick examples to help us to understand what it means for things to be dependent or independent. But let's take a look at a problem and see if we can talk it through. So here we have a student is taking a quiz randomly. So I don't know if I would advise for us to do that, but a student is taking a quiz randomly and guesses the answers to 4 different true-false questions. And so what we see here is all the different ways that they could get answers on the test. So we see on this test, the student guessed all 4 questions incorrectly, so they got 0 of the problems correct. Now, there's a lot of different ways for them to only get one problem right. Here they guessed the first question correct. Here they guessed the second question correct. Here they guessed the third question correct. And here they guessed the fourth question correct. But in each of those different outcomes, they really only got one problem right. And so this is a sample space considering the scenario that we're going to look at in solving this problem. So they're saying use this sample space to determine whether guessing question 1 correctly, so I'm going to highlight that, we're interested in guessing question 1 correctly and guessing question 2 correctly to see if those are independent. Well, if we're going to try and determine if two events are independent, let's first find the probability of them individually or independently. So let's zoom in here a little bit and let's see if we can find the probability of getting question number 1 correct. So let's go through and highlight all the options where question number 1 is correct. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So it looks like the probability of getting question number 1 correct is 8 out of 16, which is 1/2. Now, what's the probability of getting question number 2 correct. So let's again go back to our sample space and let's highlight all the options where we get question number 2 correct. So here I got question 2 correct, question 2 correct, 2, 3, 4, 5, 6, 7, and 8 again. So 8 different times we also get question 2 correct. Sorry, 8 out of 16, which is also 1/2. Now let's find the probability of getting question number 1 and question number 2 correct. So let's go through and find all of those options and see what we come up with. So which of these tests do we have both the first question and the second question, both of those correct? Well, let's see. I've got this, the second question, and the third is correct, but that's not what we're looking at. We're looking for first and second. So I'm looking for something that starts with CC. So I've got 1, 2, 3, 4. 4 of those options, whoops, out of 16, which is, of course, reducing to 1/2. Now, what's interesting here is that we know that the probability of A times the probability of B is equal to the probability of A and B if A and B are independent. So here, independent. So let's check this real quick. Do we know that 1/2 times 1/2, well, that's 1/4. Well, the good news is that's the same answer that we got here. So we know that the probability of getting question 1 correct and the probability of getting question 2 correct are in fact independent because of that multiplication equality. So that's an example where we were able to show that these two events are independent. Okay? Now let's take a look at example number 2, and it says here we're going to determine whether events are independent. So kind of another example of what it is that we were just talking about. So we have a group of 4 students, and in this particular group we have 1 boy and 3 girls, and the teacher is randomly going to select one of the students to be the speaker and a different student to be the recorder. So we're going to use our sample space, and we have the sample space listed here, to determine whether the randomly selecting a girl first and randomly selecting a girl second are independent events. Now again, let's highlight we are selecting a girl first. So let's first think about finding the probability of finding a girl first. So let's go through and highlight all the options where we have a girl chosen first, and that actually is all of these, so those first 6, and then those back 3, and so it looks like 9 out of 12 have options of girls being chosen first, so that's going to reduce to 3/4. Now, what is the probability of selecting a girl second? So again, what is the probability that we select a girl second? Well, let's go through and highlight on our sheet where do we have girls chosen in the second position. So all 6 of these and these 3 as well. So a total of 9 out of 12, which is again 3/4. Now, remember, if we're trying to determine if these two events are independent, we also need to find the probability of finding a girl first and finding a girl second, and we'll see and compare that to the multiplication of the answers above. So let's go through and see if we can find all the options where we have both a girl first and also second. So to me, it looks like these 3 scenarios as well as these 3 scenarios. So that's a total of 6 out of 12, which is 1/2. Now, if we go through and we multiply this out, 3/4 times 3/4, that gives me 9/16. And we know that 9/16 is not the same thing as 1/2. So we could highlight this and say 9/16, and we could highlight this and say 1/2. Since these numbers are not the same, then we know we can easily say selecting a girl first and selecting a girl second have to be dependent events, meaning we obviously understand that if we choose someone for the first position, we have less female students to choose for the second position. So obviously one of those events depends on the other. Okay? So that's another example or another scenario of where we're trying to compare whether things are independent or dependent. So here are a couple of example questions then. So if you'd like to try these on your own, now would be a great time to pause. If you want to just continue to watch, feel free to do so. So in example 1, it says determine whether guessing question 1 incorrectly and guessing question 2 correctly are independent events. So again, we're looking at question 1. So let's find the probability of finding question number 1 and making sure that it's incorrect. So let's scroll back up and find all those scenarios and figure out what that probability is. So let's erase these. Which of these has question number 1 being incorrect? Well, that one, 2, 3, 4, 5, 6, 7, 8. Looks like 8 out of 16. Which is, of course, 1/2. And then also we were interested in finding question 2 correctly. So what is the probability that we would get question number 2 correct? Let's go back and look at our table of events here and see what we have as options. So question number 2 correct, well, we've got a C in the second position there. 2, 3, 4, 5, 6, 7, 8. So also 8 out of 16. Which is again 1/2. And then let's see if we can figure out the probability of getting question number 1 incorrect and question number 2 correct. What would that be if we go back and find where we have an I and a C to sort of start off each of our spaces? So let's go back through and count those options up. So we're looking at an I followed by a C. So 1, 2, 3, 4. So it looks like we have 4 out of 16 there. Well, and I think that's going to kind of help us to understand, oh yeah, probability there is 1/4. We know that 1/2 times 1/2 does in fact equal 1/4. So we know that that number and that number, since they are the same, that getting question 1 incorrect and getting question 2 correct are completely independent events. The answers do not depend on one another. So these events are independent. Okay, let's take a look at a problem number 2 then. It says in example 2, determine whether randomly selecting a girl first. So problem number 2. Let's find the probability of finding a girl first and randomly selecting a boy second. So a boy in the second position. So what are those two probabilities? Well, I think we already did the girl first earlier. The probability of getting a girl first was up here. We already did that earlier, so we'll just steal that answer. That answer is 3/4. But the probability of finding a boy second, let's go back and erase sort of our marks here and which of these has a boy in the second position. So these 3, so it looks like 3 out of 12, which is 1/4. And then let's compare that with the probability of finding a girl for the first position and a boy for the second position. So let's look for a girl followed by a boy, and it is just those 3 options again that we have highlighted out of 12. So that's going to be a 3 out of 12, which is a 1/4. And because 3/4 times 1/4 is 3 out of 16, that number is not the same. So we have this number 3 out of 16, but we have this number 1 out of 4. Those are not equal, so we know that these events are dependent. These events are dependent. Okay. All right, let's keep moving then. So now we're interested in finding the probability of independent events. So if we know that 2 events are independent and we're looking to find them, then we just need to find their probabilities individually and multiply them out. So Let's read through the scenario and see if we can figure it out. As part of a board game, you need to spin the spinner. It's divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. So let's write that out. The probability of 5 and a number greater than 3. Well, that should be the same as finding the probability of a 5 times the probability of a number greater than 3. But that's only if we know the events are independent. So if we're looking at this spinner, we realize that you definitely could get a number greater than 3 before you get a number that is 5. So the order doesn't matter. And the outcome of 1 does not seem like it affects the other. So let's go ahead and work through this. The probability of getting a 5 obviously is just going to be 1 out of 8, because there's only one way to get a 5, and that's landing on the 5, and there are 8 options. The probability of getting a number greater than 3, well, keep in mind that 4 would work, 5 would work, 6 would work, and 7 would work, and 8 would work. So we have 5 different ways for that to happen. So the probability of that would be 5 out of 64. That would be one way we could express it. Or we could express that as a decimal, which of course is about 0.078, or we could express that as a percent, so about 7.8%. So the probability that you get a 5 on your first spin and a number greater than 3 on your second spin is about 7.8%. But again, we're using this idea of independence to establish that, and we're using this formula. Okay. Let's take a look at how do we find the probability of dependent events. So looking at the probability of dependent events, 2 events are dependent when one of the occurrences impacts or does affect the occurrence of the other event. And so the probability that event B occurs, given that event A has occurred, is called a conditional probability. So you have to have your condition being met in order to find that probability. And so this notation of the probability of B given A is sort of, you need to make sure you can read and understand that when you see that in problems. But let's take a look at this as a formula or as a concept. So if somebody says, find the probability of this event and also this event, and you realize that the 2 events are dependent, then you're going to be using this formula. So this would be a formula that you would be using for the probability of dependent events. So again, you're wanting to put that into your notebook and make sure you have that to access. So let's take a look at this in a problem and see if we can make sense of this. So it says a bag contains 20 $1 bills. It's a lot of singles, and 5 $100 bills. And you're randomly going to draw a bill from the bag, take it out and set it aside, and then you're randomly going to draw another bill from the bag, and your job is to find the probability that both events A and B will occur. Well, let's go ahead and read through event A. Event A is they want the first bill to be 100, and event B is the second bill. They'd also like that to be 100, so it kind of seems like it makes sense. So let's talk about this then. If we feel like these events are dependent, it sort of feels like that they are. Now, we aren't going to write out the sample space for this because we would really have a lot of options. We have 20 options for $1 bills. We have 5 options for $100 bills. We actually have 100 different outcomes for this particular problem. Meaning we could get a 1 and 100, we could get a 1 and 100 because we have 20 different ones. Each of those is counted as a separate outcome. So let's make sure we understand how to find the probability of event A. Well, if it's the first bill that we're looking for and we want that first bill to be a $100 bill, we have 5 $100 bills to choose from out of 25 bills in total. Now, the probability that the second bill that we choose, and keep in mind we put our hand in and pulled one out, the probability of event B given that event A took place, well, we assume that A took place, so there's not one $100 bill. There's one less $100 bill, so there's only 4 of those, but there's also one less total bill, so there's 4 out of 25. Now let's reduce each of these. 5 out of 25 is 1 over 5. 4 over 24 is 1 out of 6. And keep in mind, if we're looking for the probability of event A and the probability of event B occurring, then we're going to say the probability of event A times the probability of event B given that A took place, which means 1/5 times 1/6, which is, of course, 1/30. So that would be one way to answer the problem. Obviously, we could also answer it in the form of a decimal, so 0.03 repeating, or we could answer it in the form of a percentage, so about 3%. Now, what does that mean? It means the probability that you would draw two $100 bills is about 3%, because you're going to get a $100 bill on the first draw, and you're supposed to get a $100 bill on the second. So that's how you find the probability of a dependent event. So let's take a look at a couple more examples. Again, this would be a great time for you to pause if you'd like, but if you want to continue to just listen, feel free to do so. Question number 3 says, in example 3, what is the probability that you spin an even number and then an odd number? So again, if we're writing this out, probability of even number and probability of an odd number. Now, if I think about those two events, those feel like they are independent, because selecting one on the first spinner and selecting a number on the second spinner doesn't feel like they have anything to do with each other. So let's just find the probability of an even number and multiply that by the probability of an odd number and see what we come up with. So the probability of an even number, let's go back and look at example 3. It had a spinner involved. So how many even numbers are there? Well, again, we look at this and it should be pretty obvious, but we have 2, 4, 6, and 8. So we have 4 options that are even. So we have 4 out of 8 options. And obviously we know that there are also 4 options that would be odd. But let's reduce both of those before we do the multiplication. So it looks like 1/4 or a 25% chance that we would get an even number followed by an odd number. Okay. Now, in example 4, it says, what is the probability that both bills are $1 bills? So problem number 4, is asking for a $1 bill and a $1 bill. Those two events do feel like they are dependent on one another. We have to get the $1 bill on the first, and we have to get the $1 bill on the second. So we're looking at finding the probability of getting a $1 bill times the probability of getting a $1 bill given that we got a $1 bill. So the probability of getting a $1 bill, let's go back and think about what they said in example 4. They said that there were 20 $1 bills, so 20 of those out of the 25 total bills. Now, assuming we get a $1 bill in the first one, so this is where we're finding the probability of a dollar given we got a dollar. Well, there's going to be one less of those left, so we got a 19 out of a 24, and we're going to multiply this out. Now, before I do this, I'm going to try and make it a little bit easier on myself. 20 divided by 25 does reduce. They both have factors of 5 in it, so we're looking at 4/5 times 19 over 24. So what is that when we multiply that out? So 4 times 19 is 76. 5 times 24 is 120. That does reduce. It does reduce out to 19 over 30, which, you know, that's one way to answer this, but most people are liking probability problems with a percentage. So if you divide that out, the decimal would be 0.63 repeating, or we could say it's about 63% of a chance that we're only going to walk away with 2 $1 bills. So pretty good bet. You're not going to win a whole lot of money. I hope that helped. Obviously, if you have questions, please ask them. Stay safe. Talk to you soon.